So, I'm sure everybody's a bit tired, me too, I'm jet lagged. So we'll get through this, and maybe a little bit shorter than normal. We'll see. So what I wanted to do is I want to continue where I left off the last time, where we talked about model types. And the idea behind model types, in particular the box type, was that we wanted to have a type box A to be true in everywhere, so everywhere, and forever. So we extended our judgment with another context, which essentially has these assumptions in it that are of the form mu valid. Okay, and they continue to live, and in the gamma context, we have these assumptions that say x ain't true, and these assumptions may not live forever. So in particular, they will disappear when you want to actually show that M is something that is valid, that can be used everywhere. So in this rule, we wanted to say A is true everywhere. If A is true everywhere, it cannot rely on any local assumptions. And then we internalize this reasoning using the box. But the essence of this rule is really that M here is closed. And then we add an elimination rule, okay? And we worked a little hard to actually get to that elimination rule, but it is of this net form where we actually say M is of box type. Then we can save it into our forever context. Okay? So we keep the A, and then we continue to prove N is of type C. Then we actually can also eliminate this usage in case we actually have it for box A. And then there were two more rules, namely the variable rule. So the first one is using assumptions that we had previously. So if something is true right now, of course, then we know it's true. And if something was true everywhere, so it was valid, then it's also true for me right now, because it's true. Okay. And then I think I gave a little example of how we can use these ideas to do stage programming. So we looked at this idea of computing the nth element in a list, and use the box essentially to separate the program that does the generation from the program that is being generated. Right? And program generators are implemented quite often. Compilers is a form of program generation. Nada Amin will talk much more about metaprogramming, so you'll hear a lot more about that. But we can think of the box as essentially as being separating the code that is being generated, that then can be run anywhere, at any stage, at any point in the network, and the program that does the generation itself. Okay. But truly, we're not only working with things that are close. And I gave you an example the last time where I was saying, well, if I think of a recipe, and in my first step, I put in my bowl eggs, flour, and sugar, and in my next step, I say, add some liquid. And that liquid could be then coffee, milk, water. Then the type of this placeholder is not just liquid, because the liquid will be added to the bowl, and in the bowl, we already have some stuff. So we really want to think of the context in which a given placeholder lives. So here's another example. This is a very common thing. So this is a proof you might do in Nash reduction, or might look very similar if you do this kind of proof development in proof assistant like Apta or Rock. So we started out proving that A implies B implies C, implies A and B implies C. So it's a law of pairing and unpairing. And so we start out proving this by the implication rule, okay? And then we get to this assumption that says X stands for A implies B implies C. And we know that we will have here some kind of lambda. Okay? So the next step will introduce the next assumption, okay, A and B. So here we'll add the second assumption, A and B. And we know that we'll have another lambda that will be constructed. And now we need to actually prove C. And now you might say, well, how do I prove C? Well, okay, I know how to get a B, okay, because I'm going to use this assumption to prove that I have a witness in Y for A and B, and I can get out the right side of it using second. But I may not know yet how I get to B implies C. Okay. So my placeholder is essentially what this line is. That is something I don't know. You might write a question mark in a language like ACTA, for example. And so the proof term you have at this point is of this form. Lambda X, lambda Y. And then you don't know. Okay? And then you have second of Y. What is it you want to put into this proof term? Into this placeholder? Yeah?
X applied to the first of Y.
X applied to first of Y. Yes. Okay, so ultimately, what we would really like to do, and I know Zina's going to help me, hate me because everything is red. Okay. What will go in here, okay, is going to be X applied to first of Y. But you see again, right, if I plug this in here, this isn't a closed term. This is not a closed term. This depends on these assumptions, Y and X. Right, so the placeholder itself is not necessarily closed. So the idea behind a contextual type is to essentially take this judgment, and this typing judgment, because that is the type of the hole I'm trying to fill, and make it a first-class type. Okay, so, and in order to do that, we'll pair the type, B implies C, together with the context of the assumptions that we're allowed to use. So we're going to get to a contextual type. Okay. Here. Pair the context, which in our case here is X, A implies B implies C, and Y, A and B, okay, with essentially the conclusion, which is B implies C. This is going to be our type. And that means we are going to essentially reify, in this case, this hypothetical reasoning, this symbol, okay, onto the level of a proposition. We're going to lift it to the level of a proposition. So we can actually talk about these holes first class. So, well, box sounds like a good candidate. Okay, it's like it says something must be true forever. In particular, this hole, right, could appear somewhere else, and maybe I want to reuse this particular proof in some other setting. Okay. I mean, it's a very simple proof. The proof essentially says, if I have an A, right, or here in this case A and B, okay, and I have an A implies B implies C, I can strip off the A. That's essentially what we needed to prove. So. And maybe I need this in some other setting of this proof as well. So I want to reuse essentially what this placeholder stands for, and I want to make sure that this, whatever I pick, right, makes sense independently. So that's the goal. So it happens really quite often. So you might say in a program, in an even simpler case, okay, you have a camel, you might have a function written to say, well, if you plug in here something, plus 1. So the overall type of this function is going to be an int to an int. Okay, what is this hole? Okay, so think about how you would type check this. This would type check where you have x is an int, okay, because it's using it in context. Okay. And that means you would have here symbol one is an int. And since my plus, right, says that each type needs to be an int, what I will have is that this whole stands for an int in the context where I have x, that is an int. Okay, so again, I would like to pair the context, in this case, x int, with the conclusion, and it says it is an int. So this is what we're going to do today. And so we're going to introduce a new type. So our propositions or types they have all the things in it that we usually have. But instead of the box, I'm generalizing the box, to say, now it can actually be open, it doesn't need to be completely closed. And what this symbol here sort of is meant to say, we have in the papers you see different kind of notation, but I'm going to use this here on the board. This is essentially saying, pair the context by with the conclusion okay. So what is this guy inhabited with? Okay. Well, so if I go to this example over here, okay, I want to put in here something that can refer to x but is of type int. Can you give me an example of what would be such a term? X, okay, so it's inhabited by, for example, okay, simply x, okay, because we have x. What else is it inhabited with? Zero, yeah, okay, so you don't have to use the assumption, okay. What else?
Any expression of type
X to X.
X to x, okay, we could use it twice. Okay, very good. Okay, so we have x, x times x, okay, for example. So these are in some sense open, okay, but they're open with respect to this x. So we're going to add on the level of terms. All the things we have before, okay, but instead of just saying I have a box which is of type M, now the M can be open, and the things it can refer to are things from Phi. So this is in some sense like a binder, okay, like functions that bind a variable. Here we bind n variables, okay, could be more than one. For example, in here, right, we have more than one variable, maybe x and y. Okay. So in general, it can be more than one, but you can think of it as a binder, like a function, where we are binding essentially the variables that are inside, and we can use them in n. M is like the body. Question, yes?
Is there a reason we're using psi instead of gamma?
There's a small reason, okay, because I want to fix this rule, and if I use it gamma, I call it gamma, then I have suddenly two gammas, and there's no reason that these two gammas must be the same. But indeed, right, for context, I'm going to now write, I can use gamma or psi, and they're all looking like this. refer to age group as well.
Is there a special meaning to the syntax of the style of the line? I know you said it's just variant, but is there like a reason sort of historically in paper for it?
I think in our first paper, we didn't even write it like that. So I think in the first paper, we wrote it like this. Sorry. Okay. So this was meant to be the box, and these are the assumptions we were able to do. I sometimes also see, let me write psi A, maybe write these upper ceilings, okay, as an analogy for the box. I'm going to use this because it's sort of closer to what we have seen here already. And I didn't want to overload this symbol here, okay, not to confuse with this one here with this one. So I'm going to basically use this symbol here to pair the context together with the type. And it really reifies, right, this idea that you have a typing derivation that you haven't yet finished. That's what it's saying. Yeah?
Just a quick clarification, so that square there, or that box is different from the,
Yeah, that box that you want, yeah, so maybe I should write this in
what
underscore.
that box is the box modality?
So let me fix in the type. Okay, so what's the type of this guy? This guy.
Yeah.
Box. It's going to be, right? So if I give this, it's going to be a box. X, int. That's the type of this. Okay. And we're going to it's going to be inhabited by some of these terms we have down here. Okay. So we want to say that we're going to plug in something that is of this form. Box X, an int, and then maybe X times X. Make sense? Okay, or I could plug in box X int 0. Okay, that would also be an instantiation that would have this type.
And this is the same modality we've been using in generalized.
Yes.
And the box we thought had continuation.
I can't make sense of it as a continuation. It's more syntactic than a continuation. Okay. So we essentially want to sort of do a splice. Okay. So we want to splice in x times x in here. That's our goal. Okay. So it's more like composition of syntax, if you like, or syntax tree. Right? This is a syntax tree, which has a loop, which we haven't really specified, and now you want to hook up like some other tree to that syntax tree. So it's really kind of building larger syntax trees. That's what it is allowing you to do. It doesn't do any evaluation. Like continuation, I think of something that continues to evaluate. Okay. This is really purely composition of syntax.
And then, I think either yesterday or in a previous lecture, you had analyzed something to run. Was that the OS?
Right,
And
so
that's
run.
confused. Obviously, because run, I think of it as being.
Yeah, right. So run is going to be let box.
Oh,
And then we'll get some box. Okay, and we'll get to the point where how could we possibly run this guy? Okay, so I'm going to fill in these dots, okay, because we're not quite there yet. But you're pointing your finger on something, right? I mean, now I have things that are open, okay? Okay, I cleverly picked here the same variable name, x, as it was here and here. But really we want things to be stable under renaming. Okay, so that's, I think, if you're programmers, our things should be stable under renaming. So then there is an issue, okay? So how do we get this to be stable under renaming? Alpha renaming, okay, which means I could choose for this x some kind of x prime. Okay. And then I have a clash of these variables. So the splice doesn't look so nice. So this was a problem we're going to resolve in 2 minutes. Okay, give me 2 minutes. But for now, we want to basically say we have a term that is paired with its assumptions, okay, similar to a function. And now we'll need to fix our rule, so it's not closed anymore. Okay, so because we have here a context of assumptions, okay, and we have here a type that will say psi. Okay, so it's a type. It's says I'm something of type A in a context psi. So that means this M isn't closed anymore. And we just saw many examples where the psi, where M could be x times x. So what happens is going to be like a context switch. So we have here M cannot depend on things inside, so we'll have to check that M is indeed a well-type object with respect to psi. Okay. So luckily here in the elimination rule for that box, nothing really changes. Okay. So except that I'm going to write here not valid anymore, this is going to be verbose. Okay, then essentially what happens when we added it to our forever context, we're stripping off the box. Okay, so we're going to simply write here A with respect to psi, and we remove the valid, okay, because I'm getting tired of writing valid, but it is meant to say it's valid. Okay, so the box elimination nothing exciting happens. This variable rule here, nothing exciting happens, okay, because we didn't touch gamma to begin with, gamma still is there. But here in the rule where we look up things from delta, okay, something must change. And the reason it must change is that we don't have a valid anymore. We have that U stands for something that could refer to psi, and that means U does not make sense in gamma. Different things, psi and gamma. Okay. Possibly the same, but not necessarily. So to fix this, okay, we need to somehow say that we can import the things that were in psi into my current environment, which is gamma. So that is what essentially a mapping does. Okay, so we add in a mapping which goes from psi to gamma. And we're going to call this essentially a substitution. And in the proof term down here, we're going to create a closure. So that means here we have not only variable U, but we'll have a variable which essentially now is a closure of of this one called sigma. So what this means is essentially that if you wanted to use an element in here, okay, something like x times x, essentially you need to pair it with a substitution that makes sure that this x can be mapped to this x prime. That's essentially what would happen. Yeah?
So what does it mean for sigma have the same sign?
Yes. I'm gonna get that. Very good question. So what does it mean for sigma to have type psi? So intuitively, what we have is that we have here psi, and this psi looks like this. Okay. X is type A through x and a n. Yeah. So and it means that I need to, for each of these, I need to provide a witness that it follows from gamma. Okay. So what is in here is a list of witnesses where you have mi is of kind ai. So let me give this as more as an inductive definition. Okay. So if our psi is empty, okay, then we don't need to provide any mapping. It's empty the mapping. So that's our axiom. And if our psi is not empty, what we need is we need a mapping from psi to gamma. And sigma is going to be that mapping. And M must be of type A. So another way of thinking of this is the domain. This is the range. And this is the domain. Okay. And this is going to be my sigma. Yeah? This one? Yeah. So this is a substitution that maps variables from psi, which have also a variable x at the end of this context. So this is a low form substitution. If sigma is a mapping from psi to gamma, and m is of type A in gamma. So you might have seen simultaneous substitutions in other settings. Simultaneous substitutions are pretty common. But they fall out of actually a logical reading, if you like. Okay, essentially it says that we need to prove all the propositions that are in psi. And we need to prove A1 up to AN. And M1 up to Mn are these proofs for A1 up to AN. But if you like to think of this more like as a map between two contexts, it's really providing an instantiation for all the elements here inside. And all these instantiations must make sense in this range. So you can also think of this as an environment, if you like. Okay? So this would be the free variables in your environment, and then sigma is a mapping from the free variables to other terms, not necessarily values. Questions? Yeah?
So is the point of this to like model things like hygienic macros? Where
Yes. Yeah. So the point of this is really to model hygienic macros for just in general instantiations of holes that are hygienic. And what we mean usually by hygienic is that we don't have some kind of weird variable capture happening here. But rather what will happen is that the way we want to use this hole is going to be, we're going to always associate it with this kind of mapping. Often it's a renaming or a weakening substitution or the identity, but it will essentially make sure that whatever you plug in is hygienic. But it's doing it explicitly. So I'll give you an example just in a minute, so you will see how this works. I'll give you 2 examples. Okay, so, okay, good. All right, so before I give you an example for how we deal with this with meta-programming, I want to show you, I'm going to contrast some of these proofs we do here in contextual types with the original ones. So, because you might say, well, what's the big deal? Okay. Intuitively, okay, isn't it the case that I can write something like this, okay, and I'm going to make my psi just for with one element, okay, or let's say 2. Okay, so I have here A, Y, B, here C. Okay. Is it the case that this type is equivalent to the type A implies B equals C? Or the latter we already had, right? In our original box calculus. And intuitively, it's exactly the same thing that will happen. Why? Well, because what you do when you eliminate this guy, okay, so is, so let's say I start with some delta, some gamma, and you wanted to prove, okay, box A implies B implies C. Well, what you do is you drop the gamma, and you were able to prove A implies B implies C. And at that point, you do 2 introduction rules.